Thank you all for coming. My name is Kimball. I'm going to talk about real-time streaming analysis for Hadoop and Flume. We'll do a fair amount of introduction to Flume, and then we'll talk about what I really want to talk about, which is Flume-based. Flume-based is a streaming complex event processing system that's built on top of Flume. And it's designed specifically to integrate nicely in the Flume and Hadoop ecosystem. So we're going to start out with intro, motivate things, talk a bit about the high-level architecture of Flume-based, then a demo. Everybody gets to cross their fingers in unison for that one. Then we'll dive down a little deeper into the guts of how it works and wrap things up. So Flume itself is a distributed data transport and aggregation system for event or log structured data. So it's not really for bulk loads. It's not to integrate with, say, databases. That's what a system like Scoop is for. But for dealing with the systems that are constantly inputting more data or generating more data that you want to analyze in your large-scale analysis infrastructure. So Hadoop is a system that allows you to easily analyze a large amount of data that's distributed over a very large number of machines. And Hadoop does a lot of important things for you. Namely, if and when a few of those machines start misbehaving, the computation will generally succeed because it can route around these sorts of failures. Getting data into this system is one of the hardest parts of the job, simply because there's a chicken and egg issue here. If the data is large enough to be worthy of processing with Hadoop, it's being generated in a large-scale distributed fashion. So you need to have fault tolerance before the data gets into the fault-tolerant processing system. That's complicated, and that's what Flume does. So Flume is a system where you put nodes on a bunch of machines. So these machines on the left here might represent a bunch of web servers that are constantly generating access logs. And each time somebody hits a website, we get an event or a message in one of those logs, and we want that message to wind up in HDFS on the right. So Flume will run a process called an agent on each of those machines, and those agents then take the messages and forward them along down the chain. Of course, if you have hundreds of web servers or more machines generating some sort of data, having that many machines connecting to Hadoop directly would be a scalability bottleneck. So Flume allows you to have intermediate tiers that it calls collectors. The agents all connect to a collector, send their data there. The collector then takes all of those different streams, batches them together, and then writes a consolidated stream of data to the true endpoint. So some terminology that gets involved here. Both collectors and agents are actually referred to as nodes. Within a node, there's actually a concept of a physical node, which is the Flume process. And then there's a logical node, which represents a channel of data. And each of these logical nodes has both a source and a sink. A source might be something like tail the file varlog httpd access log. And then the sink would say, where do we want the messages from that source to be put to? So an example sink might be, go to the distributed file system and write out to a file in the logs directory. And there's a number of macros that can be used, so we're actually going to write separate subdirectories for every day and every origin host. So we can get a nice partitioned data set ready to go inside of Hadoop. There's a number of different source and sink implementations that are available. Tail will constantly read the end of the file, as you might expect. There's the ability to take an entire file. You can also do things like, say, integrate with log4j, where you take the messages right out of a logger and push that directly into the system. So when you have a three-tier system like the one shown over here, there's a sink called the collector sink, which opens an RPC channel to another machine that has a collector source, which is listening for RPCs. And that's how you can move data through multiple hierarchical levels of Flume before it gets to its true endpoint. One of the things that makes Flume different from other distributed log collection systems, like, say, Scribe, is the way that it deals with configuration. So this configuration system is actually pretty deeply tied into its fault tolerance notion. So instead of simply connecting to a single collector, machines can actually connect to multiple collectors. You can have there's probably actually 100 servers in this column. You might have, say, 5 collectors in the middle. The agents can all connect to different collectors randomly, and if they start failing to forward data to one of these collectors, they can switch to send the data to a different collector and still get to the endpoint in HDFS. The way that these agents all know when a machine is up or down is because everybody is connected to a master node in the system. And so the control plane is illustrated on this slide in orange. So all of the machines send a heartbeat message back to the master every few seconds, indicating that they're still alive. And on the heartbeat response that the master sends back, it can also tell one of these machines to reconfigure itself with a different source and a different sink. This is in contrast to a system like, say, Scribe, where every machine is statically configured with a config file that was deployed via a system like, say, Puppet. So you can connect to the Flume master via the console, which is talking over a thrift protocol to it. So you can tell the master, I want to reconfigure a given node, send its data elsewhere, and then the next time that node sends a heartbeat back, it will get a message in response that tells it to update its configuration, and it will remap its outputs to wherever the operator has requested. So within single-digit seconds of data being generated, it's moving through this system. If you're using something like a Log4j connector, then it's going to be in milli or microseconds available within Flume. If you're using one of the sources that tails a file constantly, then that tail source is going to check every couple of seconds, 1 or 2 basically, as to whether that file's been updated, take those new messages and push them into Flume. So we have a real-time component to how Flume operates. It doesn't wait for large batches of data, but instead tries to keep up with the data and is more or less I/O bound on the network in its capability to do this. So data, you've got a lot of it, and it's moving into a system like Hadoop, and you want to analyze it. But despite the fact that our data is moving in real time, our analysis can't be. Hadoop-based analyses typically run every night, every few hours. If you are on sort of the cutting edge of things and you have your pipeline very condensed, you can perhaps get this down to once every 5 or 10 minutes. But ultimately, you're not going to be able to do MapReduce analytics any faster than that. And that's unfortunate because there's a lot of reasons why we might want to analyze this data on the fly. If people are running ad campaigns on your website and they have set a maximum budget, you want to know when all of their clicks and ad impressions have hit their maximum so that you can cut them off and move to the next campaign so you can most efficiently move your ad inventory. If you're running some sort of e-commerce platform, you want to be able to do personalization and recommendations in real time. If somebody's searching for restaurants on your website and you figure out what neighborhood they're in and that they like pizza, you don't want to still be showing them generic ads. You want to be showing them things for pizza or things for the neighborhood they're in while they're still on the site, in the session. You can also use this on the back-end side of things for operations, load and performance monitoring. If one of your servers starts spitting out huge volumes of data into the error log, you want to understand that and set an alert pretty quickly. But Flume doesn't grant us this capability. It's a transport layer and not an analytic system. So there's no ability in Flume to inspect the actual contents of these messages, or events as they're called in Flume. There's also no notion of aggregation or rolling counters, or frankly even filters. This leads to all sorts of, shall we say, fascinating hacks around this to recover some sort of real-time analytic capability. At one place that I was talking to the engineers, they've got it so that Flume will send the data both to HDFS and to a system like MySQL. Then on a cron job, every minute or so, Python script will kick off a SQL job, which will take the roll-up of how many ad impressions they've consumed in the last minute, and then they push that information into the web backend. And as you might imagine, this is a somewhat brittle process. And I've talked to people at 5 or 6 different organizations, and they all do, I've heard 7 or 8 really different ways of doing roughly this sort of thing out of that many people. So it seems like there's a real need for an analytic capability on top of this. So we need to do analysis, and people seem to be using SQL-like systems to do it. So what do we have to work with? First, one of the advantages of Flume is that it's very pluggable. The sources and sinks can load their definitions from jars that you insert into the system without actually having to recompile Flume itself. And unlike systems like, say, Scribe, you can reconfigure the transport topology on the fly. Within seconds, you can get a server sending to a different sink. And finally, the contents of Flume events are uninterpreted, meaning whatever bytes that we want to push into the body of an event, we're free to do so. So we can define a new endpoint for Flume data, we can store arbitrary data in the event itself, and using the Thrift API, we can reconfigure Flume automatically and programmatically. So instead of taking something like MySQL and using that as an endpoint, we can introduce a server that I'll call FlumeBase. And FlumeBase will consume an event stream from Flume, allow you to apply a continuous query over that information, and the output of that query is another set of events that are being made visible as if they're coming from an ordinary Flume source. So the output of this is still inline in the Flume topology. We can send that filtered or aggregated result into HDFS, or we could send it to some sort of online consumer. For example, if we wanted to alert, we could write a Nagios endpoint and send it there. We could also send this sort of straight back into the web backend if we need to update our online ad serving infrastructure, etc. The Flume-based server itself is controlled by a client which will connect to it to submit queries and possibly view their output as well. So these queries are persistent queries. In a SQL system, a conventional SQL system, you would connect to the server, you'd submit a query, and then you'd wait for the response. And if the client were to hang up, the server would actually just throw the query away. But that's because the query is expected to consume a finite amount of data, produce a finite response, and deliver it back to the process that requested it. In FlumeBase, we're working over infinite streams of information at all times. So the queries themselves also have an infinite timeline associated with them. So clients can submit these queries that run persistently, generating new output in the Flume transport network waiting for connections. And we can connect to and inspect the output of one of these queries either immediately after submitting it or at any other later time. When we need to pull in more source data from different Flume sources, the Flume-based server will transparently go to the Flume nodes that are providing that information and reconfigure them to send their output to both their original destination and to the Flume-based server. So you don't have to do any operational work to integrate this into the online topology. And as mentioned, the output looks to any consumers of it just like the input itself. Flume-based queries are actually written in a SQL-like language called RT-SQL, and it's very similar to SQL. It lowers the learning curve, and frankly, it's pretty expressive for most of the sorts of things that you'd want to do. So instead of saying create table, you might just say create stream, which defines an infinite stream of information that's pulled from some Flume-based source. So we give a name to the stream, call this one foo, and then we define the makeup of the message body itself. So we say that this message body is going to contain 3 fields, status, message, and priority, and we can assign data types to these. Not shown in this, because it's using the default, is how we then parse that information. So this will assume that it's a comma-delimited text-based event, but we can actually give further specifications that expect a different delimiter or expect Avro or JSON encoded information or a different method of parsing the information altogether. And finally, we have to tell FlumeBase where to get this information from. So we say that the foo stream is based on the output of the Flume node backend server 5. Once we've defined a stream, we can then do queries over it. One shown here will filter the information, returning only the information that has priority level 10 for whatever that means in this invented business case. RT-SQL provides us with most of the standard features that you would expect to have in SQL. Select queries where you can do filtering with where clauses, you can do aggregations with group by, you can filter on those aggregates with having clauses, and it also supports the ability to join different streams together. Because these streams are infinite, both group by and join need you to define a window in which they operate. So you have to specify that you want to do a rolling group over, say, the last 5 seconds, 1 hour, or so on. And within a window, you can apply the standard aggregator SQL windowing functions like count, min, max, sum, average, etc. All right. So I think I've spoken about this enough, and to give you a true sense of how this works, we're just going to go use it. So the first thing we're going to do is start the server itself. So this is going to define the backend process that is going to actually execute the Flume-based RT-SQL queries. New window. Then here, we're going to actually connect a shell to this. The shell doesn't do anything particularly complicated. It mostly just ferries text back and forth to the server. So currently, there are no streams defined in our system, and so we have to tell Flume-based where it can get some information from. So we can do create stream s. So I've told Flume-based that there's a stream named s, and we're going to have two fields in it. It should expect an integer and then some string. And instead of telling it which node we're going to get this data from, we'll tell Flume-based that it should host a Flume node within its own system, a local source that's going to tail a file named foo. And over here, make sure that I don't have foo. Good. All right. So then I'm going to just say, all right, select star from s. So this has initialized a flow. A Flume-based query compiles into a flow, and we're expecting to see timestamped events that have an ID and a message field. So now I can say, put some messages into the file foo, and if we go back to our shell, we can see that these messages are coming back out. We're continually tailing this file. So if we add more data, we see this in the Flume-based world. So now we can drop that flow, and we can do something a little more interesting, where we can actually filter the information. So there's a few basic functions that are put in there that you can apply to columns of the data. So we only want to look at messages where the text portion of the event has more than 5 characters. So that's a short message. Here's a long message. We get the long message out, not the short message. So with this one, we're actually going to try, now we're going to really cross our fingers, to do an aggregate. So what I'm saying here is we want to know how many messages are being pushed out of this source, this tail of this file. And we want to know what the count is over a rolling 2-second long window. So if I submit this, we're only going to get the count star out. We're not going to get any of the actual field bodies themselves. And the first thing it's going to do, because we're reading from a local source, it's going to restart the tail. So we've got 5 lines in there, and so we start out by saying that we have 5 in that last 2-second window, which is all the time leading up to now. Now we can put a whole bunch of messages in here, and we start to see we get an increasing number of events. But if I put messages in very slowly, we see a much lower rate over that rolling 2-second long window. One of the most powerful features of Flume-based is the ability to export its results as a new Flume stream, which, of course, since Flume-based can read Flume streams, means that it can also take this information and read it back into itself. So what we're going to do next is we're going to create a stream in terms of another query. So we're going to read the ID field, which is just an integer. We're going to double that. And the output stream is going to be a stream named doubled. So we started this flow. And in a second, we're going to see all of those things, all of those message IDs times 2. So we had a whole bunch of 5s going in there that come out as 10s. Now, by default, whenever we put a query into the Flume-based shell, we see its results on the console. So we can see what our running queries are by typing Control/F, and this lists our existing flows. So flow ID number 4 is what is creating this streaming doubled, and we can see over on the right the actual query that was used for it. And because of this asterisk over here, this shows that we're actually watching the output of that on our console. Oh dear, we're back. So we can unwatch that flow, and if I look again, we don't have an asterisk. So now if I were to push some more messages in here, no data on our console, but they are still being executed and being pushed to the Flume endpoint. So now I can say, I can use that output stream doubled, and I can run a select against this. So I can select 3 times A, and now you're watching this other flow. So now if I echo the value 1 in there, we get 6 out. 1 turned into 2 via the doubled stream, we select 3 times 2, we get 6. If I put in 12, we should get 72. So similarly, I can show you that if you launch the Flume shell, which allows you to administer the Flume master, we can connect to the Flume master. I'm going to type get configs, which tells us what the configuration looks like. And here we can see that it's created an internal node that it was using to host that tail source, and that's what's powering flow number 4. But it's also created a node named doubled, which is exposing the output of that create stream as select back to the rest of the Flume world. So, how's this actually working under the hood? The block diagram here shows the major actors in the Flume-based architecture, and I'm going to just go over these sort of in the next couple of slides. On the left, in purple, we've got the client process, and it's talking to the RT-SQL compiler. Objects in purple are operating on text. Objects on the right, in blue, are the actual flows that are being executed against the stream of events that are being operated on. And then down on the left here, we've got this green object, which is what's actually interacting with the Flume topology, reconfiguring nodes, creating logical nodes on the fly, etc. as needed. So when we start out in the client process, and we type in a query like select star from S, the client has no idea what it's actually doing. It simply takes that string and ships it over to the server and asks it to compile. The RT-SQL compiler then consults the stream dictionary to see what does S actually look like. We had defined that earlier. We had defined a set of fields which are in there, its schema, and implicitly we had also defined how to parse it. We could have explicitly defined a parser that had a different delimiter or expected a different input data type like JSON or a regular expression, as well as where to get it from. We had said a local source, which was a tail source. We could have also said from a node, from a local file, etc. Taking all that information, the RT-SQL compiler then takes the string-based query, compiles that into an abstract syntax tree, and then turns it into a directed acyclic graph of logical steps to execute to satisfy this query. In the future, these logical steps will probably be more optimized. Right now, there's not terribly much intelligence going on there. But from this logical graph of operators, we actually then compile that again into another DAG, which is the physical operators. So these physical operators might be a hash join or execute a filter, which is to satisfy a where clause, so on and so forth. These physical operators are what we call a flow. So once we've established what the flow of operators to run over the events are, it pushes this into the execution thread. The execution thread is then hooked up at the top to another thread which is hosting a Flume node which will read data from somewhere else in the Flume network. and on the other side, another thread which is hosting a different Flume node which emits its output back to the Flume network at large. And you can have many of these flows running in parallel, pulling from different sources, executing their outputs, and emitting to different output logical nodes. If the client were to disconnect at any time after submitting the query, the Flume-based server would continue to execute these flows, reading from Flume sources and generating a Flume output node without really any disruption. You can drop flows explicitly using the d/d operator like I showed earlier when a given flow is no longer interesting or useful to you. So event data can enter Flume-based in any format, but that's kind of challenging to deal with all by itself. There's a schema associated with each stream, which tells us which columns we expect to be in there. So we assume that it's a roughly columnar world, but not quite actually. There are types that will handle both lists and maps within a given column, in the same way that Hive can have both lists and maps inside of a given record, in addition to just the scalar columns that you'd expect from a regular database. But actually transforming that into an internal representation that we can use is the responsibility of something called the event parser. So there's a delimited event parser, there's an arrow event parser, a regular expression event parser, etc. All of these different event parsers emit output records that are in a common format, which is based on Avro. So by taking the input schema, I said ID is an int, message is a string, then this uses the Avro generic serialization system to create a new generic record that has an ID field, which is an integer, a message field, which is a string, and so on. When we are passing events through the elements of the flow operator DAG, we are actually using Avro serialized data in Flume event instances. So downstream elements of the flow can just pick out the ID field, and they'll know that they're getting an integer because the Avro system is preserving the types all the way through. If you project from one schema to another, select only a subset of the columns, then it will go through a projection operator that takes in one Avro input schema and outputs a different Avro schema that has only the fields in it that you require. And then these final output events also have Avro binary encoded bodies. So you can take the output of this Flume stream and emit it to an Avro file in HDFS, for example, for later bulk analysis over this real-time filtered data set. The system interacts with Flume basically at the endpoints and as lazily as possible. So when we create a stream, all we're doing is saying that we're just representing that we have some stream coming from a source that we could query. And that we know that if we queried it, we know what its schema would look like. It's only when you actually submit a query against that stream that it actually connects to the Flume nodes that provide that data and reconfigure them to send their output both to their original destination as well as to the Flume-based server. So we try to minimize bandwidth utilization and only pull data from other nodes when it's really necessary. When we drop a flow, we're reference counting how many flows we're pulling from a given source. And when that hits 0, the controller inside the Flume-based server connects back to the master again and reconfigures the upstream source to connect only to its original output sync, instead of to the original sync and the Flume-based sync. Question?
So a query over a 10-minute window would take 10 minutes to return the first time? It would be initiated, or am I missing something?
Yes.
I am missing something?
No, you're correct. That the first output will be 10 minutes after the input. And it's actually rising edge triggered, so if you have an idle period on the input, then you're going to get nothing on the output until more input data sort of pushes it along. Sort of just another note on the way that the aggregation works is that it's actually using bucketing to make rolling windows. So by default, there are 100 buckets over your time span. So if you ask for a 10-minute window, then you're going to have 6-second wide buckets. And the granularity of the count star is every 6 seconds would be the most frequent that it would emit a new output count. But each actual count would be over 100 buckets wide. of data. And you can actually tune the number of buckets if you want with the parameter, but that's just what I thought was a reasonable default. So the granularity of your query scales in conjunction with the time window that you're operating over. So another sort of nice architectural principle here is that the notion of a server is actually abstracted away in Flume-based into something that's called the execution environment. So we can run everything in a single process if we want. The client can connect to the local execution environment, which just runs in another thread inside the same server. And we can actually even embed a Flume master and its nodes in there as well. So for testing, working on a laptop, you can just do everything inside one process. You can also use the Thrift execution environment to connect to the remote server-based execution environment, which currently is a single process. In the ideal world, Flume-based itself would be able to operate over a fleet of machines and distribute queries, doing the group bys over a number of different nodes, which were each taking a different sort of hashed partition space of the messages. And if and when that day comes, that will be in some different distributed execution environment that you can load into all those different machines. The ability to have different execution environments allows us to take that logical plan and compile that into a physical plan that is specific to the environment in which it's operating. So, in conclusion, real-time analytics is an important use case inside of sort of any large-scale big data infrastructure, but using Hadoop and MapReduce to do it is the wrong way to go. You really do need to have a specialized system that is tuned to actually working with real-time information. Flume is providing us with a really adaptable transport layer that can work with this, and SQL provides us with a reasonable set of constructs for expressing a fair number of the queries that we would actually be interested in running in a real-time fashion. And once we do that sort of initial relational work on the data, then we might want to then put it into a system like Hadoop, put these roll-ups into a system like Hadoop for offline analysis over the aggregates. Hope that this was helpful, and I hope that you would all check this out. So please go to flumebase.org. There's a sporadically updated blog. There's some documentation and binary distributions. You can just download a tarball and run it in Linux or OS X or probably even Cygwin if you cross your fingers hard enough. And it's reasonably matters included. There's a sample data set, walkthrough, so you can get up and start typing queries in just a couple of minutes. All of the source is Apache 2 licensed. It's at github.com/flumebase/flumebase, and contributors are welcome. And I think that we've now got about 5 minutes for questions. Thank you for attending, and let's do that.
Are there any limits on message payload?
Flume itself has a message payload which is compiled in, which defaults to 32 kilobytes per message. You can override this if you recompile it.
Is there any initial benchmarking? I mean, I know it's like 0.2 and stuff like that, but how many messages is that people to get out of this thing today?
Yeah, so this obviously depends on, say, messages, the message size, as was mentioned, as well as the complexity of the query. But I think I did one test where I got 150,000 per second moving through, where it was just like select star, and I think that dropped to about 100,000 once I actually started trying to do some computation over the elements within there. Of course, if you then filter messages and say you have, say, 10% selectivity, it goes up by some huge factor. So there's a wide range, and frankly, there's, I'm sure, a huge amount of low-hanging fruit to optimize away, because I bet that I do at least a dozen buffer copies more than I should be.
Do the queries interact with any like reference data, standing data? Can you like go out to a MySQL database and
Not right now, but they should. Right, so it should be possible to do a continuous join against a static lookup table or something, but not yet.
Did you consider using sort of open source event stream processing engine like Esper?
Yeah, so
like growing your own?
yeah, so I thought about that, and looked at a couple other options that were also sort of just not really appropriate. The problem with Esper really is the GPL nature is problematic for a lot of users of the Hadoop ecosystem. which is a more or less entirely Apache 2 licensed world. So it's kind of the realm that people will accept systems in there.
Yeah, I mean, that's a shame, because they go quite a bunch of cool features.
They do. No, Esper is absolutely a considerably more robust and mature system. But it's also, I've heard a lot of horror stories from people who've tried to integrate it with their infrastructure, but also a couple success stories. But you know, the purpose, the goal here was really for users of Hadoop and Flume and the rest of that particular stack to just have something which is sort of seamlessly integrated into that environment.
Well, I've sort of done everything that you said should not be done here to solve this typical problem. And what I do is I sort of use Scribe, write files onto HDFS. They get rolled over every minute, and then write the queries using Ping to generate the aggregates. And the end-to-end turnaround time is about 2.5 to 3 minutes from when the event actually occurred. What's really working out well for us is the scalability side of it, because you know the whole setup is completely horizontally scalable, but it's still like 3 minutes away.
Yep. Let's see. Let's go right to left.
If you have an existing Hadoop cluster, is this something you're just tacking on alongside it, or is this 5 more nodes that you're going to need to run that kind of stuff? What's kind of the deployment?
I mean, CPU cycles have to come from somewhere.
Right.
So it has to live on a physical host, right? It consumes resources there, but it doesn't require a terrific amount of configuration. So you can certainly set it up for testing purposes, kind of anywhere.
Just like you did it on your laptop, right? You just
Yep.
set up one box that's doing that stuff.
Yep.
But what happens in your example when you write messages to that file that's being failed that don't reply to the IP comment message format?
It does the best it can. So it will try to parse from left to right, and it will insert nulls into fields that are not, you know, if you start writing out, like, say, text into the first field where it's supposed to be an integer, that'll just turn into a null.
Are you familiar with IBM's System S enclosure streams? And is that how it influenced or you know,
I know that it exists, and that's about the extent of it.
Okay, you've invented a lot of it, so there you go.
Thank you all for coming.